Electricity is incredibly well behaved, right up until it absolutely isn't. You plug something in, flip a switch, and everything works perfectly. No sparks, no smoke, no tiny lightning spirits escaping the outlet like they've been evicted. Life is good, but behind that calm surface, electricity is constantly flirting with chaos. It's always asking a very dangerous question. What happens if I show up with more voltage than you were expecting? Because sometimes it does exactly that. And when excess voltage appears, it cannot just hang around awkwardly like an uninvited guest. It must go somewhere, or things start glowing, melting, or making sounds that mean turn it off immediately. I'm Professor Everything, and today we're answering the question: where does excess voltage go? Right here on Explaining Everything. Let's start by fixing one very common misunderstanding. Voltage is not electricity itself. Voltage is electrical pressure. It's the force that pushes electrons through a circuit, not the electrons themselves. If electricity were water, voltage would be the pressure in the pipe. More pressure means a stronger push. Less pressure means a gentle nudge and a motivational speech. Your devices are designed to handle a specific voltage. Give them the right amount, and everything flows smoothly. Give them too much, and electrons don't knock first. They kick the door in and rearrange the furniture. Here's the important part. Voltage doesn't get used up. Current flows. Energy gets converted. Voltage simply exists as a difference in electrical potential. So, when we talk about excess voltage, we're really talking about extra energy trying to force itself through parts of a circuit that are not emotionally prepared for it. And physics hates inefficiency almost as much as it hates cheap chargers with lies printed on the box. When excess voltage appears, the first and most common place it ends up is heat. Lots of heat. Every electrical component has resistance. Resistance is friction for electrons. And friction means heat, whether you like it or not. When the voltage is higher than expected, several things happen very quickly. Resistors warm up. Wires heat internally. Components experience stress, like they're trying to hold in a sneeze during a job interview. In many circuits, this is intentional. Voltage regulators, transformers, and resistors are designed to safely convert extra energy into heat. They're basically electrical bouncers, calmly escorting excess voltage out of the building. That's why power adapters feel warm. They're not malfunctioning. They're performing electrical crowd control. But when the voltage rises too high, heat increases faster than common sense disappears on social media. Insulation melts. Solder liquefies. Silicon chips experience what engineers politely call thermal failure and what users call it's dead. At that point, excess voltage hasn't gone anywhere productive. It has turned into pure thermal regret. When circuits need excess voltage gone immediately, they send it to ground. Ground isn't a magical void. It's simply a reference point with a stable electrical potential, often connected to the Earth itself. Electricity flows toward it because physics loves balance, and the ground is very good at absorbing chaos. This is why surge protectors dump excess energy into the ground. It's why power supplies rely on ground paths. It's why electrical systems bond everything together like an overprotective family reunion. when a voltage spike occurs, whether from lightning, switching loads, or power grid issues, protective systems redirect that energy away from sensitive electronics and straight into the ground. Ground doesn't store electricity. It spreads the energy across an enormous area, turning something dangerous into something harmless. The Earth basically takes one for the team, which is generous considering how often we step on it. Sometimes excess voltage doesn't politely leave through heat or ground. Sometimes it gets stopped aggressively. That's when sacrificial components step in. Zener diodes clamp voltage by conducting extra energy once a specific threshold is reached. Metal oxide varistors absorb sudden spikes and slowly destroy themselves in the process. Fuses break the circuit entirely because they believe in dramatic but effective solutions. These components don't negotiate. They see excess voltage and immediately say, "Nope, absolutely not. I volunteer." And yes, sometimes this involves sparks, pop-in sounds, or that unmistakable smell of burned optimism. That wasn't a random failure. That was excess voltage attempting to go somewhere illegal. Energy never disappears. It always turns into heat, light, mechanical damage, or redistributed energy. Physics does not offer refunds. So where does excess voltage go? It doesn't vanish. It doesn't teleport. It doesn't wait patiently for permission. It gets converted into heat. It gets redirected to the ground. It gets absorbed by protective components. Or it escapes in dramatic, warranty-voiding fashion. Electrical systems work because engineers assume excess voltage will happen. They design escape routes for it, like emergency exits in a nightclub full of electrons wearing leather jackets. Electricity is obedient, but only when you give it somewhere safe to go. So the next time your charger feels warm, your surge protector clicks, or a fuse sacrifices itself heroically, remember, that wasn't a failure. That was excess voltage being handled professionally, by science, with consequences. If you like this video, hit that like button and subscribe. Also, if you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. If you enjoyed this video, please check out our other bingeable channels. Thank you for tuning in and join us next time here in the channel that answers all the why, what, who, where, and how questions you've always wondered about here on Explaining Everything.